sir.
Oh, wonderful. So we can start.
You
So,
can
Yes, sir.
start.
yes, yes, I was actually very happy to see the title actually today of this uh, summer school, winter school, I believe. Innovation in microbiology for sustainable food production, right?
Yes, sir.
Yes.
I am SFP and very much related to our activities, and I think this the second lecture topic is well fits in that. That is fermentation technology for production of value-added product. And I'm sure that several other uh, faculty members will be covering this topic. But I will be talking more from the food technology perspective because this is what the work which we are doing here. You know, so what morning actually I was talking about the fermented food, where we have basically seen the ability of a microorganism to convert the raw material or the substrate into value-added product. Now we are using the same microorganism, but we are giving the substrate a very specific substrate. There it is a more complex substrate. But here actually we are giving very specific substrate and looking for a very specific end product. There we look in general the more generalized end product. Okay, so the previous lecture and then there the product we are using for a consumption. But here the product can be used for any other industrial purpose. So that is what are the such industrial purpose we will be using this value added product. I will be explaining you people subsequently. So we have basically seen the fermentation what it is, the conversion of substrate into the value added product happens because of the action of the enzymes. And now when we understood this, the science behind that, the technological levels, people started using that for the industrial production. And that has actually required the several steps. That includes selection of efficient microbial strain. So this is actually the important step. So how you can actually select the efficient culture available and naturally through the mutagenesis or through the recombinant created technology or any other method of the strain improvement. You are now going to pick up or select the more potent culture which is actually fits your requirement. Second is the culturing. How you are going to culture, whether it is aerobic or anaerobic or solid state fermentation, like this. And then more importantly, how you maintain the pure culture. So that is also important, right? Because you will be looking the end product only from derived from that microorganism or through that microorganism and not from the other contaminant. And if there is a possibility of a contamination, then your end product or the finish, your output will be affected. The next one, when we look for the industrial production of any metabolites, we look for the preparation of suitable media. Now, actually, with reference to the microbial product is concerned, one of the major hindrance is the cost of a media, because most of this microbiological media found to be expensive, especially when you are producing in a bulk, in a larger scale. So how you can actually look for economically cheaper media or suitable, more useful. The media which will give actually the maximum, right? The media which will have specific precursor, I can say, like this. And then subsequently you look for something like the fermenter. So optimization of fermentation parameters, which is more important. Where the pH, the temperature, the agitation, the aeration, you know, the BOD, all these things actually plays the important role. So how much surface you are exposing, what is the oxygen concentration, how long the fermentation you are going to carry, all these things. Then mass production in the large scale production. And when we are actually looking for a production of some specific metabolite, so how you can actually purify from the culture medium or from the interest from the cell, So if it is from the cell, then naturally your product will be contaminated with several intracellular solids, right? So how you can actually efficiently purify from the other components of this, either cell debris or from the media component. So for a simple layman to tell what the fermentation is, that any organism, including the human being also. Of course, when we consume the glucose, it gets converted into pyruvic acid by the process of glycolysis. So everyone knows. But in case of microorganism, this pyruvate either goes for the lactic fermentation or alcohol fermentation in general. There are the different other pathways also. Here, in a simpler word, I will tell. In a human being, we see the Krebs cycle or PCA cycle, and then followed by oxidative phosphorylated. No, and then this is how the ATP gets generated. But when you give when you give glucose to any microbial system, they convert this pyruvate into the value added intermediate, which we call it here either the lactic acid fermentation or alcohol fermentation. And then you see this lactic acid by the aspergillus, you can get the soya sauce. If you add in the lactobacillus, it is there, then yogurt and cheese, dairy product, or it is Saccharomyces, bravery, bread making yeast, you get this product, bread. Then the brewing yeast will give the ethanol. This is how actually the end products gets converted. So you give the microorganism either in the form of glucose or maltose or molasses or the starch. You basically get like this kind of the end product. And this property we are going to use in a larger scale. This property we are going to use for our benefit. This property we are going to use to make the end product industrially in a larger scale. So what are actually the key requirements? So one is of course the production strength, and then when you are choosing the production strength, you look for the high yielding strength. We ensure that it is stable biochemically. Should not produce any undesirable substance. So I am talking about that microorganism which you are going to use for the industrial purpose for the production of any metabolites. Then it should not produce undesirable substances, and more importantly, it should be easily cultivated on large scale. You have to cultivate in large scale. Then the production media, it should be suitable chemical compositions. Then there should have the precursor. I will tell the precursor when I will talk about the antibiotic production. Then that production media should have the buffering capacity also, and then it should not have the foaming, free from toxicity and then any contamination also. Other parameters, as I told previous slide, with reference to the fermentation parameters, the temperature, what is the optimum temperature, right? Where the maximum production is there, the pH optimum, then oxygen availability, similarly the water activity. So all these things actually matters when we are actually looking to produce any metabolites using the microorganisms. So here are actually some of this list of microorganisms and their fermented products are described. We have already covered two products, but you can see Propionibacteria, cheese making, Aspergillus lactobacillus streptococcus, cheddar cheese, yogurt or soya sauce, Saccharomyces for the beer or wine, Escherichia coli Acidobacter, acetic acid, which is basically vinegar, Clostridium, nail polish removal or acetone or isopropanol. Now, some of these participants may wonder that lactic acid or acetic acid or even isopropanol can be chemically synthesized. Yes, chemical processes are well established and found to be cheaper, but they are not actually environment friendly. Then the biological processes has its own advantage of their environmental perspective as well as producing in the large scale. So what are such actually product we are actually producing in industrially by the fermentation? Antibiotics, of course. So what are the antibiotics we get in the pharmaceutical sample of pharmacy? You see whether it is penicillin, streptomycin, tetracycline, solution. All are actually the product of the fermentation technology. Then vitamins like vitamin B12, B2, vitamin C. Most of these vitamins are again from the fermentation. Yeast, you get the press yeast. What you prepare for the pizza or brewery yeast, or the baking yeast, or you get actually now the biomass which is they dry it, and then it is used. Then organic acid, similarly, as I told, that this some of this organic acid actually can be produced even in the by the method of chemical synthesis. What do you see? We can actually through the industrial production using specific organism, optimizing the fermentation process, looking for the specific metabolites, and then you get the organic acid like citric acid, lactic acid, acetic acid, amino acid, more important, glutamic acid. When we talk at that time, I will tell you again about especially about the glutamic acid, which is used as a sweetener in food industry. Single cell protein from the bacteria or algal and these things. Then now several enzymes by the solid state fermentations are the submerged fermentation being used by produced by the several fungal strains, amylases, proteases are there, pectinases are there. Then some of the solvents, ethanol, alcohol, glycerol, butanol, and microbial insecticide also like Beta-toxin, right? And then of course the morning what we covered is the fermented food. There's no fermented food industry if it has to produce in large scale. So in India we don't prepare except the dahi or curd. But if you see the kimchi, the way it is produced in a large scale, the sauerkraut in a very large scale, the sausages, big industries will be manufacturing this kind of products. And of course, the alcoholic beverages also everywhere. So, with reference to talking about the antibiotics, we have of course the synthetic antibiotics also, like nalidixic acid. But then there are several antibiotics which are actually penicillin here, or the semi-synthetic which they are actually derivatizing, from the synthetic one. So here are actually the examples of several such antibiotics, like the peptide antibiotics is the bacitracin, antifungal is there, this one, or nitrobenzene derivative, chlorphenicol, vancomycin is from streptomyces. So all these antibiotics are produced by the process of a fermentation. Now here I will be coming actually with reference to the peptide antibiotics, giving our one case study. Now here is actually the case study with reference to the penicillin, which is the first antibiotics produced or used in the world, and discovered in 1928. So the organism used is you see here penicillium chrysanthemum, and when we are actually producing such high value product to reduce the cost of production, it is actually very important to look for a specific precursor, because this precursor will actually help to enhance the production or to obtain maximum product, end product. Okay. Then similarly, you see here the media, the constant liquor, because once you use the agro industry waste residue, your cost of production will be. Similarly, the lactose, glucose, calcium carbonate, potassium, edible oil, precursor with a slow feeding rate. So all this, the specific organism and the high yielding strain, the precursor, and then typical production media, all these things actually matters to obtain maximum yield from during the fermentation. And how this is done? You see here, preserve the culture. So you have the laboratory stock culture, grow that one in 1 liter, then you scale up that one to 10 liter. Then subsequently you produce in the seed storage like 100 liter, 1000 and 10,000. And then after this 10,000, directly add in the production stage, so that you have the minimum contamination and immediate production, means growth of your producing strain with the minimum contamination. And this is how actually freeze-dried, the experimental plan is described here. Just for a second. If anyone has any question there, I will be happy to just clarify it. Dr. Sone, any question, clarification? Hello? Anyone can respond me whether my presentation? Can
Yes, sir. Good afternoon, sir. You're audible, sir.
okay, okay, okay. So I was telling about how the citric penicillin antibiotics is produced industrially, and then how you can actually cultivate the fungal from the spores. Then you have the stand, and then plastic culture, and then seed condition, then production fermenter, and then you have the mycelium, and then you filter, and then you get this finally, and this is how penicillin is produced industrially. Here is actually the second case study with reference to our own work, isolation and characterization of a lasopeptide. Okay. So the microorganism which we use, the Bacillus lichenicollis, Bacillus, the spore forming bacteria, and this culture was isolated from the goat milk.
Excuse me, sir. Your voice is not audible, sir. Sir, your voice is not audible.
Hello. Uh, Hello, Sure, ma'am. Uh,
Can you see my slides?
yes, sir. Yes, sir.
So I was actually previously I was explaining about how penicillin is produced commercially by the means of fermentation technology. Is it okay? Somebody has to answer me, then I can tell about the second example.
Yes, sir.
Yes. Now I am talking with reference to our own work, production of a lasopeptide, okay, by fermentation. And our initial experiment showed that this bacillus culture produces a lasopeptide, a ring-like structure at the end with the lasopeptide, and we have seen its antibacterial activity against Salmonella typhi. As well as several other foodborne pathogens also. More important, it inhibits the Mycobacterium tuberculosis type activity. Yeah. So what does it mean that it inhibits RNA biosynthesis? Because this inhibition here, you can see here Mycobacterium smithmatis, one of the species of Mycobacterium. It inhibits, you see, a very big zone of inhibition we could record by the activity of a herbal culture. So this peptide is of 2.3 kilodalton, around 20 amino acids. And no, this one, 1.8 kilodalton. And then we have one more from Bifidobacterium. So this one is from Bacillus, the lysopeptide, and we have one more lysopeptide from Bifidobacterium breve. And more importantly, to tell you people is that both are actually the probiotic cultures. Okay, and their mode of action is inhibiting RNA biasing. So you will not see the antibiotics which inhibits RNA biasing. Those faculty members, those who are actually from the molecular biology or biotechnology, they will know how the relevance of any antibiotics inhibiting RNA biasing, because that antibiotics can be directly used for treating the TB, Mycobacterium tuberculosis. That's what I'm trying. So what did we did is, you see our subsequent study. Of course, these do not have much connection with the fermentation, but just I am explaining that we try to purify, we check their antibacterial activity, and then we have actually done the whole genome sequencing and identified the genome, the gene cluster also for product. Now, so this is what the gene cluster is actually described here. Okay, this antimicrobial peptide from Bacillus we use for the purpose of reducing the salmonella infection in rat. Very important study. So we actually fed the rat with the salmonella and this antimicrobial peptide of Bacillus, and then we could see that the animals get protected when from salmonella infection when they are co-fed with this lysopeptide, no? And they could actually recover the salmonellosis problem when we administer them the lysopeptide of this bacillus. No? So the infected one, salmonella infected one, could recover as a normal upon feeding with the lysopeptide of bacillus. This is what the experiment here is. Okay. This is actually the another peptide from again the bacillus, basically the two peptides which inhibit the several gram-negative pathogen also. And then reason because of this culture has this bacillus culture, Bacillus subtilis SC3.7, has a ability to produce two lanthanum containing antibiotics. One is like sublikenine type, and another is subtilosin. And due to this reason, we could see the inhibition of several gram-negative pathogens like Klebsiella, pneumonia, Shigella, and then Salmonella is not interested, I think, here, but several such gram-negative pathogens also. Yeah, this work was actually in this public journal. We actually characterize this peptide by mass spectra, and then we could actually see this. So to do all this kind of work, you need that the substance should be produced in a large scale, in a more amount, and it should be free from much contaminating media, and should be produced in a shorter time, in other words. Now I am coming back with reference to the production of a value-added product by the fermentation technology. One of such products besides the antibiotics is the organic acid. Okay. And then several of these organic acids are produced, like acetic acid is there, formic, lactic, succinic, citric acid is there, propionic acid is there. All are produced by the fermentation technology using the specific microorganism. Like for the citric acid, we use the aspergillus. Lactic acid, we use the lactobacillus. Acetic acid, we use acetobacter. Gluconic acid, we use again the aspergillus. Pyruvic acid, succinic, tartaric acid. All the list of microorganisms are given. So here is actually the case study with reference to the citric acid production. Okay. And then you can actually see what is the microorganism used, it is the aspergillus. Then surface culture of submerged fermentation media is described here. And then why we need the citric acid, means what are its applications. So you see, it is being used as acid in the food, chelating and sequestering agent, production of carbonated beverages, and citrate and citrate esters as a plasticizer also. How the citric acid can be produced, here is the procedure. So you have actually, it starts, as I told you in the beginning itself, that all this work actually starts with a particular strain of microorganism. What is the strain which is used here? Aspergillus niger M101. You use any other Aspergillus, maybe you may not get that much. You may not be able to cultivate in a particular media. You know, you will have another problem. Then when the stock culture, then you will be subculturing potato to extract agar is the media used for the cultivation in a laboratory. Then inoculum development from the spores. Then you do for the fermentation. And then once you have done the fermentation, after you see 192 hours, now with the shaking, now you have to speed up to 100 RPM. Then you do the fermentation, filtration, and then that supernatant will be the citric acid distillation. So you will get the supernatant liquid, which will have the citric acid, and another is the residue, cell biomass. Okay. So this is what actually the citric acid is produced industrially. One of you also, most of you people also can try like this kind of the procedure, and then see how the microorganisms can help you to get such a value-added product. Similarly, the enzymes, most of this now, Biocan is there in India, Novozyme is there. All they produced by the methods which I am explaining here, like amylases, aspergillus, glucomylases, aspergillus niger, proteases, lipase, cellulase, aspartase, catalase, all fungal strains because fungus is a more potent than the bacteria also for production and more robust also. Okay. So here is actually the case study which refers to the amylase product. So what is the organism? Again the same. The type strain, the culture which has been mutagenized or improved or selected properly. Okay. So for the amylase, the fungal strain or the fungal includes like Aspergillus niger or Aspergillus origin or even the Bacillus licheniformis. Okay. I have given the example Bacillus licheniformis we use for production of peptide antibiotics. Here you see some other strain of Bacillus licheniformis you use for the amylase production. Now you see amylase binds is inhibited when the medium contains the glucose. How the substrate inhibition has been identified, right? And then you see cornstarch activities. Cornstarch or corn strip liquor, because this work has to be the very cheap. And as I told you initially, the media cost is one of the major hindrance when you are actually looking at the production of any metabolites within the microbial system, like this way. So once you get such amylase, what you are going to do? So you can see it can be used for the detergent industry. So whatever we are actually getting, the washing powders, it will have actually the amylase. Okay. Whatever the washing powder you people use at home will have the alpha amylase in that. Paper and textile industry, this is here. Bioremediation, anti-foaming activity, bioethanol production, brewing and yeast also. Yes, the starch saccharification and liquefaction industry. So several such application alpha amylase has. Why? Because we have the abundant starch in abundance. This conversion how it starch get sacrificed, and you get this small monomeric unit called oligomeric unit. And this oligomeric unit actually has the several applications, in industry. So after the alpha amylase, next is the amino acids, And in the beginning, I was talking about the glutamic acid production by Carnobacterium glutamicum, because this is where actually the biotechnology has revolutionized in Japan. The production of glutamic acid by Carnobacterium glutamicum. Okay. Now, for what purpose actually amino acids in general are required? Because they are actually are important class substances living in the living organism, and production of amino acids through fermentation was initiated by Himashita Shita and his co-workers in 1956. And this was nothing but from the glutamicum, glutamic acid in the process. Okay. So you will see here the several different products can be produced, like the glycerol is there, the starch, sugars are there, all these things you put these raw materials, you will get the value added product. Okay. How glutamic acid is produced industrially, here is actually that case study described. The organism which used is a Corynebacterium, as I told, and then media should have glucose or starch hydrolysis, raw material for fermentative production. Fermentation is carried out at 40 to 48 hours. 30-degree temperature. You see, all these parameters are known in German. Now pH is given here. Media composition, then all this. What you are going to do with the glutamic acid? So you see, as a flavor enhancer, as I told Mami, then to improve the flavor, then cosmetic industry like a restaurant. I hope my voice is there. 1 minute, I will just check.
Yes, sir.
Okay, okay. Yeah, because sometimes if disconnection is there, then becomes a problem. Deepika J and AMI Patel have raised the hand. I don't know for what purpose. So this is the glutamic acid production as I was explaining you. So glutamic is the bacterium, and then you see once they actually use by this test contrast microscopy, you will be seeing them like this. Vitamins very much important. Otherwise, you have to take the tablets. Vitamins, no. These are actually produced by the phototropic microorganisms, but few organisms excrete vitamins in the greater sections, and then more importantly, the vitamin B complexes, vitamin B from B1 to B12, produced by the lactic acid. Okay, so you have in general the vitamins, the water soluble and then fat soluble. Everyone must be knowing, and what the water soluble are, the A, D, E, K, and water fat soluble, and then water soluble are B and C. Right? How vitamin B12 is produced? So you see, the microorganism which is used, not the lactic acid bacteria. Some lactic acid bacteria have the ability, but then they are actually you need much more complex media. More simple media for the microorganism which can grow in a simpler media like bacillus is there, pseudomonas. But actually ensure that they are not a pathogenic, okay? Or cyanocobalamin, which is again vitamin B12 also named as cyanocobalamin. So you have the procedure in the sequence for the B12 production. And you see, every day we actually need 0.001 milligram means I think it should be some one 1 microgram per day. Actually, you need the vitamin. Okay. But we are for what purpose it has been used? Acts as a antidote for cyanide poisoning. In case of cyanide poisoning, this can be actually used as antidote in the treatment of pernicious anemia. Because vitamin B12 deficiency is very common even in India. Also. Responsible for reducing the brain shrinkage, very useful for brain development. Helps in healthy regulation of homocysteine control. So several useful applications are there. Now, how this is being produced in the fermentation? So in fermentation, we have something like upstream processes where you will be developing your the primary inoculum, then fermentation, and then downstream processing. So downstream processing is nothing but the product recovery. Okay. So the product recovery is already described here how you are going to reduce the product. So with this, I actually conclude here. We can have some 5 minutes.
You're not audible, sir.
You people be informing me. Of course, I am in the last slide only now. Can you see my PPT?
No, sir.
Now, can you see?
Yes,
Can
sir. Yes, sir.
Okay.
Yes, sir.
So, with reference to the conclusion of this presentation, I was talking the ability of a microorganism to produce an array of metabolites. Same organism will not produce, or one can produce one or two, not all, in a larger quantity. What I'm trying to say. And then this most of this metabolite has all these health benefits. That is what I was trying to tell. This one. And what I'm trying to tell with this third point is that we have actually very high diversity of microorganisms, exist in the nature, which is actually untapped or required the subsequent studies. When we are actually producing this metabolites from a microorganism, what we have something called the scale-up studies, large scale or fermentation production, and then when we actually look to produce in a large scale, there is actually requirement so-called the high precision. Why this is high precision is required? Because the cost of production of a microbial metabolites is very high, not very high compared to the chemical or engineering approaches. Okay, synthetic approach I would say. Okay. So that's why reducing the cost is actually one of these major challenges these days. Then I actually would like to conclude with reference to the advanced technologies of AI ML that can be explored for the production of value-added products through the fermentation technology route. Okay. So with this, I am concluding my presentation. I hope it was convincing to most of you people. If you have any question, I will be actually happy to answer. So I close the presentation so that we can see the screen properly. Yes. Question, please, from Dr. Sonia Kumari, Chika J, and Dharmendra Shukla have raised their hands.
Yeah. Good afternoon, Dr. I was just keen to know, to request you to highlight the regulatory requirement to use the native diversified microorganism isolated from Indian subsoil, as well as some GMOs to be used.
Exactly. For the regulatory aspect, the native organisms, that we supposed to have for industrial production the approval from the National Biodiversity Board, which is in the Chennai, National Biodiversity Authority. If you are using for the industrial purpose, for the research purpose, there is no harm. We are also taking the sample from the different habitats, isolating microorganisms, studying their enzyme production, antibiotic production. But if you are using commercially, or if you are actually patenting that, or if you are actually sharing with other investigator abroad, so we need the permission for the NDA. As far as the metabolite is concerned, if it is for the food, it should be the grass status microorganism. Then its a preclinical trial should be done. Its a virulence should be non-pathogenicity should be tested and all. If it is for a clinical, then we have the DCGI is approved. Director DGCI, Director General of DCGI, Drug Controller General of India, approval, and for that naturally you need the substance with high purity, its safety data, and then preclinical as well as the clinical trial demonstrated for its efficacy, and then safety also.
Okay, thank you.
Any other question? Deepika J. No. The last question from the Dr. Sonia Kumar, and then we close the presentation. Somebody typed in chat box, I think. Question? No. So no more questions. Now I could see the 34 people are there. This is the morning 50 were there. So if no more questions, okay. Patel wants to ask, I believe. No? So if no more questions, then I close.